Well, hey, hello, and welcome to Sky Tour Radio. This is Mark D'Antonio here, and over there we have Daryl Mason, and down there we have Tara. How are you, Tara? Uh-oh. He says, hold on a minute. Okay, well, how are you, Tara?
My mic was muted. I'm sorry.
Okay. Daryl, how about you?
I'm good, thank you. How are you? Hello, Tara. How are you?
Hi, good. I'm so glad to be here.
That's nice to see you guys.
Yeah, excellent.
Yeah. And I just want to welcome everybody here to Sky Tour Radio here on KGRA. We're actually Sky Tour Radio is an offshoot of Sky Tour Livestream, which is our live deep sky observatory, which, if it's clear tonight, we will be running. So look for that on YouTube, and you'll look for the alerts and notifications. What is Sky Tour Livestream? Sky Tour Livestream is this remote observatory that I run from here in Connecticut. It's in the Arizona desert. And we bring these beautiful deep sky objects to your screens, wherever your screen is. You can have it on a large screen TV like many people do, or on their computers, even on their phones.
Little tiny phone.
Right, even a little tiny phone shows it well, right?
Just as beautiful.
Yeah, and so what we do is we actually show beautiful vistas, things like this. Okay, this is the Lagoon Nebula on the right, and on the left is a little-known Chinese Dragon Nebula. And this is all part of Sagittarius. It's just beautiful. And we show really cool things like this. This is a dead star. It's called the Helix. It's something that we look at often. We actually just imaged this one the other night, and I think it was your idea, Daryl, to do this one.
Yeah, that's what we finished tonight with the other night.
Yep.
It's getting to be that time of year.
It is, isn't it?
Yep. I mean, that's among the stars of fall, I guess you'd say.
Yeah. And this is a really eerie-looking dark cloud of gas and dust in Taurus, called the Taurus dark cloud. And these dark clouds are my favorite places in the universe because they're the springboard of life in the universe. And the springboard, the locations where stars will be forming and planets will form around such stars. Now, we also get stars that form in stellar nurseries like this one. This is the Orion Nebula in the bottom part and the Running Man Nebula at the top. You'll notice all the brownish red dust all around it. This is a really dusty place in the universe. And when the stars do wink on, as they did in that lower part of the nebula and in the upper part of the nebula, they cause the nebula to glow or to reflect light. And we get these wonderful colors that we see. And we go through all these and talk about them. And you see this image. This image actually looked pretty much like you see it straight out of the observatory. So people saw this live as we made it. I think, I don't know, Tara, have you joined us on us? You've joined us, right?
It's been a while, but yes.
Well, that's going to change, right?
Daryl,
we got to have her on because Daryl's always there with us.
More than usually.
Yeah.
Awesome.
Yeah. And, this is the Cave Nebula, this beautiful dark cloud with this gorgeous stellar nursery making the hydrogen glow red. It's a beautiful location.
Cepheus?
That is correct.
Okay, I remember.
And then we have this one, the Trifid Nebula. This is a gorgeous dual nebula. It's an emission nebula at the bottom, which makes the hydrogen is glowing reddish. And above, the stars aren't hot enough to cause the hydrogen gas to glow in that region, but the dust in that region does scatter the starlight, and the starlight that it scatters favorably is the blue light. So that's why these nebulae are blue, and they call them reflection nebula. So these are really cool places. There's the seagull. These are all stuff we've recently imaged, by the way, within the last weeks or a couple months. The seagulls we did I think last winter, but we've got new techniques now that we're using to help process, so you can see more detail live in the telescope than we've had before. So it's really neat. And then this guy here, what's that look like to you, Tara? What does that look like?
Oh, it's like something erupting. It almost looks like a big rock, too, on one edge.
Yeah.
Brains.
Yeah, it looks like brains.
It is brainy.
Brains.
Yes. Peeled brains.
Nah, I love that thought, but the truth is, I think it looks like a jellyfish as well, and that's what this is called. It's called the Jellyfish Nebula.
Okay, I see the legs and stuff.
Right? You see that? Tentacles?
It looks very soft like a jellyfish, definitely, and a brain.
Oh yeah. Now this next one, this is a re-image of one we did before. Is this gorgeous one? That one, you got it, Daryl. That's called LDN 1622. What?
Okay.
Loon's Dark Nebula 1622 is the actual catalog name, but what it is also colloquially known as the Boogeyman Nebula.
Pretty spooky.
And, it is, and I have it oriented the correct way here. So this is just some of the things you can see if you come to our live observatory, and you can actually see these things right on your screens. And then they all go to an online database in seconds. So you can actually go see these pictures, download them for yourself, all for free, and do whatever you like with them.
Very cool.
Yeah. And if you if you want, our portal that we use, that we created, is called skytourlive.com. So skytourlive.com, man, that's it. And Tara, of course, is very important to the process because she is part of the organization as well with Marianne Robb. And we actually started a 501c3 organization with SkyTour in order to, further getting, grants and possible foundation support for doing what we do.
Mm-hmm.
So, we're kind of underway. And of course, Daryl over there, he's always the voice on SkyTour live stream with us wherever we're on.
And I interrupt you constantly.
Well, if you have something to say, you've got to do that, right?
Yeah, have to get a word in edgewise.
Well, let's be honest. I come from a performing background, and I know that dead air is bad air. So we always have to have something in the background. That's why I have music. And we can play music tonight too, but I'm not going to do it. Okay, we have it on this too, but it's too early on. So anyway, this is what you get. And again, like I said, head to skytourlive.com or skytourlive.org and check us out. Now, tonight on Sky Tour Radio, you know what we're going to talk about, Daryl?
Supernovas.
Yeah, we're going to talk about novas and supernovas. That's right. Isn't it interesting how the same process that creates the nova also creates a supernova in some cases? Interesting. And the interesting thing is what the difference is,
Are there micronovas?
Maybe in my head, but that's about it.
Okay. Never heard of them, but I got it.
That's okay. What were you going to say, Daryl?
Big bada boom.
Big bada boom. Yeah, that's exactly right. Now, I want to share my screen because I want to show a few things here while we're going. Now, one of the things that I think is really cool about the universe is that the universe throws all kinds of things at us, things that we just don't expect, right? And one of them is this right here. Okay, this right here that you're seeing. This is a beautiful double star in the constellation Cygnus. It actually forms the head of the swan in Cygnus, the swan. And the star is known as, Tara, do you know the name of the star?
I do not.
Okay,
I
well,
should.
Daryl, I know he does.
Of course he does.
Right.
Eh,
Yeah. It's
Alberio.
Alberio. You got it.
Of
Alberio.
course. I've heard it.
Yeah. Well, Alberio is a beautiful double star. What's neat about this star,
Wow.
yeah, oops, that's the other thing I was going to show you.
Ooh.
What's neat about this star, let me go back in and zoom in on it again, is amongst all the other stars that you see here in Cygnus, and this is just a few of them, not even remotely a lot of them.
Ah, there it is.
But if we zoom in on this now, you'll notice this star is blue and this star is orange. This is a star known as a B-type star. Now, the stars are listed in order of temperature, basically. And what that means is that when we have a diagram like this one that we chart our stars on, you look along the bottom and you see it says OBAFGKM. Well, that's the hottest and bluest is the leftmost, and the hottest up to the top. You see it makes a snaky line down through the center and down diagonally to the right. And the M stars are the coolest and the smallest. Those O stars, right, and B stars are very hot, and they give off a lot of ultraviolet radiation, and that's what we have here. This is a B star, right? And paradoxically, right next to it is a star that is actually very different. This star is down in the K end of that scale at the bottom. So we have one that's a B-type star on the left side there, and a K-type star on the right side there. Very interesting. And but together in the sky, they make perhaps the most beautiful pair of stars I've ever seen. Daryl, you had some comments about Alberio in the past. I'm not trying to put you on the spot, but I mean, as a pair of stars, we look at them at the distance that they are from us. They're separated by 5,000 astronomical units. Now, an astronomical unit is the distance from the Earth to the Sun. And 5,000 of those is a very, very huge amount, considering Neptune's 30 astronomical units away.
Yep. It's a big universe. There are many really nice binary or multiple star systems out there. In fact, I forget what the count or the ratio is nowadays, but it's like 1 in 2 or 1 in 3 stars we see is actually a member of a multiple star system. Yeah. Some of them are really pretty. We should pursue that more sometime, perhaps. But I think binaries can get kind of boring after a while. Some people love them, and some people specialize in them.
Yeah. Well, it's binary stars that form the crux of the things we're going to talk about tonight, too. Because when we look here, these two stars are far enough apart so that they don't interact with each other. They're going to be independent, right? They're not going to interact with each other ever, okay? Because they're a very large distance away from each other. And when one of them gets very, very large as a red giant, eventually, in fact, the K star, the orange one, is actually a giant star. And the blue star is not. It's a regular hydrogen fusing normal type star, just hotter. But as time goes on, that'll change. But some of these stars are actually quite close to each other. And when we look at the stars that are quite close to each other, one of the things we have to consider is that you might have a situation, right, for instance, where gas actually leaks out from one star and goes to another. And you can say, well, how can that be? Well, it comes down to a situation like this.
Cool.
Yeah.
Is that real?
No, it's an illustration, but it is interesting because eventually we will be able to see this in a manner of speaking. Not from James Webb, but at some future telescope, we'll be able to capture something like this. Now, this is a star. The one on the left here is a red giant. It has used up all its hydrogen, and it's expanded into a red giant as it starts to fuse other stuff it has. And as it does so, it reaches a point where the gas that's far, far away from the star can leak onto a star that had previously gone through evolution and shrunk to a white dwarf on the right. All right. Now, that's how this happens. All right? And now you might say, well, how can that possibly happen? Why would it do that? And it's because when we look at this red giant, okay, we have to say, well, the red giant has expanded really, really large. If you put it where the sun was, it might go all the way out to Jupiter. You can imagine that the material way out there is only loosely gravitationally held by the star at that point. So it stands to reason that that stuff out there just needs a little tug to go somewhere else. And that somewhere else depends on the red giant having what's called its Roche lobe, this dotted line here you see on the left, filled with that red giant. Beyond that, the material in the red giant's outer atmosphere could leak through the central point between the two stars and get pulled onto the white dwarf. And that hydrogen that's leaking through that central, what they call in the bottom there says mass transfer stream. That's the mass transfer stream. It goes onto that white dwarf. And what happens is at a certain point, that hydrogen on the surface of the white dwarf can spontaneously begin to fuse. And when it does, it gets extremely bright and we get what's called a nova. Okay. So that happens when we get that spontaneous fusion on the surface of a white dwarf. Boom! This stuff just blows off and then it dims down again and it starts all over again. The star is still intact. Now that's interesting. Now, you might say, well, wait a minute. We've talked about these type 1A supernovas where a red giant does exactly the same thing as we're seeing here. But the result is that the white dwarf explodes. So what's the difference? Why does it make a difference? And what do you think, Tara?
I can only think that one is super. And that's the difference. One's a supernova. It has to do with the pressure, doesn't it? And the gravitational collapse and
that's all part of it. Darryl, what do you think?
Well, the white dwarf is gaining mass as it accumulates the overflow from the companion star.
This one right here, yeah.
Yep. And if that mass exceeds 1.4 solar masses, you've passed the so-called Chandrasekhar limit, and the star is going to go supernova.
That's right. Okay. But the question is, how come we get a nova sometimes and not a supernova? And that answer lies, and you're on it, Darryl, lies with the mass of the star. So if the star reaches that magic number Darryl was alluding to, and that's this number, the Subramanian Chandrasekhar limit, which is 1.44 solar masses. Okay, M0 was the mass of the sun. So at 1.44, that's the Chandrasekhar limit. And that limit is the maximum limit that a white dwarf can have. Beyond that limit, a couple things can happen. Now, and here's how it works. This is what's weird. All right. When the white dwarf reaches the Chandrasekhar limit, it's a delicate balance point because the star can go into spontaneous fusion and blow up and expel its contents to the universe. Or, as the findings are showing now, it might actually collapse into a neutron star, which we know only happens with more massive stars. So the way it works is if we have a white dwarf that's, say, only 1.2 solar masses in size, and it begins accreting matter in this manner over here from a red giant near it, it might only get to, say, 1.3, 1.34 solar masses before it goes into that fusion arena where it does this massive spontaneous fusion event, gets really, really bright, and now the star is still there. Okay, but if it's low mass, in other words, it can do that, and we'll get just a regular nova. But if the star is a one that's, say, 1.3, this is confusing. If it's a little bit more massive to begin with, then the star can accumulate this hydrogen gas. But because it's accumulating it, other things that are going on inside are changing the makeup of the star. You got to remember, white dwarfs are held up by something called electron degeneracy pressure. They're so compact that it's just the electrons, the free electrons in that star that are pushing outward, right? There's no fusion going on inside the star, but there's conversion of particles from one to another going on. And so if we have a white dwarf that has enough mass, then its core can start converting some of these electrons to neutrons. And it can do, of course, millions of them at a time and keep going. And if it does that, there might come a point where the star has less and less electrons, and so the star will start to collapse a little bit. Meanwhile, it's accumulating mass in this manner here from the red giant next to it. Okay, but it's accumulating mass, but it's starting to collapse. And then it could reach a magic point where it may not reach 1.44 solar masses before it starts this terminal collapse. And it starts this terminal collapse because many of the electrons are gone, and that degeneracy pressure pushing out, holding that star up, goes away little by little. And now that star can collapse into a very, very bright blue, hot neutron star. Now, in the other case, where it goes, as Daryl said, to 1.44 solar masses, and it doesn't make enough neutrons in its core fast enough to collapse it into a neutron star, which seems to be mostly what happens, then the star simply gets destroyed in this cataclysmic explosion that we call a supernova. And there's a special name, it's the type 1A supernova. So we're learning a lot about supernovae out there. A lot of new things coming to light. So I think that's kind of where you were heading with that, Daryl, talking about the supernova, the 1A. And Tara,
I have a question there.
Yeah.
When you say the electrons are converted into neutrons, the mass of the white dwarf basically forces the electrons onto the protons, converting them to neutrons. Correct?
Yeah, that's correct. It's like it's a natural process that will occur, but you have to have enough of it going on fast enough to overcome the speed at which this accretion is going on through this other process we showed here.
Yeah.
Okay. And if that speed is fast enough, if neutrons are getting made fast enough, then the star can start to collapse, and it gets to that terminal phase where it's going to collapse now into a neutron star. And it can be above 1.44 solar masses at that point and not explode because it's made more neutrons. And now the neutrons will support the weight of the star, the mass of the star, and be pushing outward with their own pushback force called neutron degeneracy pressure. It's really phenomenal. It's controversial, okay? But they just found a white dwarf actually in the news, which is about the size of the moon. And it's the most massive white dwarf seen to date.
Wow.
So it's possible that this white dwarf, the size of the moon, normally we talk about them being the size of the Earth. Okay. But this one's the size of the moon. And the thing about white dwarfs is the smaller they are, the more massive they are. Okay. Because if they're massive, they contract. So this is an ultra compact object. And there's a range of sizes. But the behaviors are, have been pretty consistently understood until now. So it's really interesting that this one could be one of those ones, white dwarfs, that actually goes into being a neutron star eventually, because that mass is actually most likely causing neutrons to be produced with the protons and the electrons in the core of that star. So that's pretty neat, isn't it?
It's so cool.
Yeah.
So much to know.
Yeah, well, there's so many things out there that are changing, right? And with the James Webb Space Telescope, which is probably a favorite of mine and Daryl's, we absolutely love the James Webb and what we can possibly learn from it, So there's a lot going on out there,
Yeah, it's the Webb's like trying to drink from a fire hose. I mean, there's so much coming out; it's hard to keep up with.
I know. That's exactly right, and that's true. And honestly, I don't know. I don't know when it's going to end because we're learning more and more and more now. So everything we're talking about here is for a binary system where you have two closely orbiting stars. One's a white dwarf. Now they were both normal stars at one point, and then one just moved into a red giant phase, and then shrunk down to white dwarf without affecting this star. And then this star now, when it went into a red giant, well, now we had a white dwarf which has a limitation on its mass, and it starts feeding mass in. And based on the conditions, we can either get a Type 1A explosion where you get a whole, beautiful stellar remnant left in the night sky, or we can get a neutron star, which could be the source of very, very high energy, ultraviolet energy, and maybe even, X-rays. Or we can get a nova, which will just periodically, burst into the scene and then dim out, and then burst into the scene and then dim out. So there's three things now that white dwarfs can do that are really interesting.
I have a question along the line of all this.
Yeah.
Do we know what kind of supernova the Crab Nebula supernova was? Was it a 1A or a?
I think that was a core collapse.
Okay, because I seem to remember reading somewhere recently that they think that the remnant in the middle of the Crab Nebula may be a double star.
I remember seeing that, and I think they were talking about with the James Webb. They were talking about the Southern Ring Nebula as being a double component. You remember that?
No.
Okay, because the Southern Ring Nebula is actually a closely spaced double star, and they didn't know that until James Webb could image that star very, very clearly.
Cool.
So that might have been what is. I don't think the Crab pulsar, I think, is a lone star. If it was a double or a binary, I have no idea. I've never heard that.
I'd have to look that up. I seem to remember seeing that somewhere recently.
Okay.
I have a question. Do nebula, when they explode, do they contain large chunks of rocks or anything, or is it just all gaseous? And does it collapse into form? You see the stars in there, but are there pre-planets or anything? What would you call that? I don't know.
At most, you're going to get dust, right? When I was showing you this picture, let's see, right here, okay? This is dust that came from, in part, a supernova explosion at one point or another. Okay, every nebula we show that has this dark dust in it, that dark dust, for instance, came from a supernova, a red giant that made this soot or these silicon-based grains and carbon molecules, carbon molecules, and sprinkled them throughout the interstellar medium. Okay. So when a star explodes, at most you're going to get some of those molecules that are in the far reaches that might survive that explosion for a period of time. But they recombine later to form things like planets. You have to imagine all these dust grains are microscopic. They're in a few size of a few microns, which is 10 to the minus 8 meters. I mean, they're really, really tiny dust particles, all right, that end up congealing and conglomerating together to make larger ones. And then particles of dust, which then become little tiny pebbles, which become stones, which become rocks, which then congeal together to form asteroids, which then maybe form a solid body. It goes molten, and they all melt together, like it happened on all the planets in our solar system. The rocky planets. So, in our understanding, that's kind of what happens. With planetogenesis. I made that word up. Planetary genesis.
Are there rocks in the cores of some gaseous planets?
Interesting. Yeah, but we don't know specifically. We think there might be like iron nickel cores in many planets. Okay, in Jupiter, we know that there's metallic hydrogen at its core. That might be the outer core, but they probably have a very small rocky core that started as a seed object, because when they first formed, they probably formed in a dust cloud like these dust clouds we're talking about. And so they most often probably had a rocky core to begin with, and then the rest of the stuff, the gas and everything, gravitationally bound and so forth, created these planets out of the solar nebula, the original, bath of materials from which the planets were formed.
They used to say that they thought Jupiter had like about 4 Earth masses of a rocky core, and latest numbers I've seen on that just the other day, I saw they're thinking maybe 10 Earth masses now of a rocky core in Jupiter.
Yeah. Well, I didn't know the latest numbers.
The gas has to have something to be attracted to focus on to start building a planet.
Well, with a star, the gas only is attracted to other gas. So if you have a star that doesn't ignite, it means the temperature in the core doesn't get high enough. But that core could all be metallic hydrogen. It could be, it doesn't have to be rocky. Brown dwarfs aren't necessarily have a rocky core. Our sun certainly doesn't have one. But most stars don't have that kind of core, rocky core at all.
I'm sorry, did I say star? I meant planet.
No, I understand,
but there's a continuum to all that too. That you got little planets, big planets, and great big planets, and you get super Jupiters, and you're headed towards brown dwarfs.
That's right. And the brown dwarfs may or may not have rocky cores, because they may have just been accreting hydrogen gas and potential small amounts of other gas, right? And so they're big hydrogen balls. And of course, they're going to be hot in the center, but not hot enough to start fusion. So now you got this collection of hydrogen gas that can't do anything. It can't ignite and become a star, but it's not going to be a planet because it doesn't have the proper constituents to make up a planet. So it's always going to be this hot mess.
A Pluto?
Gas. Yeah. Well, yeah, no. Well, Pluto is actually a planet that's icy, right? I mean, it's got water and nitrogen.
Well, is it a planet or not? That's what I was joking about.
Oh, yeah. Well, there you go. Yeah, you're absolutely right.
Heck yes, it's a planet.
Yeah. You guys notice I talked to Clyde Tombaugh at an astro conference back in my early astronomy days, and we talked about Pluto as a planet, and he was very proud of that discovery. But even then, he had the foresight to suggest that more research was needed to confirm it. But he did believe it was a planet, and I did too.
And as far as gas giant planets go, Jupiter and I think Saturn also, well, they're not to the point of even being brown dwarfs, but they do put out more energy than they receive from the sun. I assume that's due to gravitational effects.
Yeah, it's certainly due to, well, it's also due to any radioactive elements that formed within it.
Yes.
Yeah, like our Earth. I mean, residual heat from formation is still present. But we also have the heat of radioactive elements brought into proximity with each other, like in our Earth. That's really one of the primary sources of heat for our planet in the core. Is these radioactive elements as well as the residual heat from formation.
Yeah, I seem to remember hearing Jupiter emits like 3 times as much energy as it receives from the sun.
Well, I believe that it's a massive ball of gas, and it's very hot in the middle, and it's got a very, very dynamic weather system. Right? We see these clouds change all the time.
Everything's always compared to Jupiter too, it seems like.
It's convenient because for us it's the biggest planet in the solar system.
Yeah, it's like 318 Earth masses, right?
Yeah, it's big. It's really massive. So now going back to stars, we talked about how white dwarfs can do a nova, become a neutron star perhaps, or just do a supernova, a 1A supernova explosion when too much hydrogen builds up too quickly and the star goes over that critical Subramanian Chandrasekhar limit of 1.44 solar masses. But The other type of supernova that's really interesting is the core collapse supernova. And this one is, I think, one of the more interesting ones, because this is the reason why most of the elements, appear in the periodic table. If you notice, you'll see exploding massive stars up there in yellow. Look at all the yellows in the table. Okay, that's where many of those components come from. But look at merging neutron stars. Many of the heavier elements, okay, are in there: gold, silver, okay, osmium, all right, polonium. Okay, all these are additionally created there. And then, of course, in the whiter ones, we have exploding white dwarfs. You'll see that the heavier elements seem to show up from there, as well as some of the lighter ones, like titanium can be an exploding white dwarf, partially, as you can see. This gives a good idea where they all come from. Really kind of cool. And stars like in the green, dying low mass stars, those are interesting because a dying low mass star can create some of these elements as well. Now, here I am telling you that, stars can only fuse up to number 26 in the table there, which is iron. And that's true. But there's another process that stars do, even stars like our sun, that is a much slower process to actually create some of these additional elements that we see in the periodic table in the green. And that's something that, we've talked about before, but it's actually known as the slow process, or the S process. And that's, again, that's a process of decay where, it's called neutron capture decay, where the neutron gets converted into a proton. Here we are talking about protons and electrons converting into neutrons to make a neutron star out of a white dwarf. But you can also get protons created from neutrons that get decayed and held in a atomic nucleus as well. And that's how we get in these low mass stars. We get these additional elements. So you see, it's a slurry of building blocks that we actually learn about here, Now, in a massive star, we actually end up with a hydrogen star that's fusing into helium right in the core. And they very quickly run out of that hydrogen in these massive stars. Well, then they start, fusing helium into carbon, okay, and oxygen. And each time they do that, when they start to run out, they begin to shrink a little bit. And now they're dredging more material down toward the core that can be used as fuel. And then they find a new fuel source. Hey, we've got more hydrogen. Let's start burning again. And it makes a shell of hydrogen. And then it brings down when it runs out of that, it brings it down. It's still burning a little bit of hydrogen. It comes down and expands again when it starts to burn helium. And it keeps doing that. It will pulsate. And as it does, what it does is over time, it ends up with these shells. The core ends up being like these stratified layered shells. And this is what that looks like. Okay. So we actually have on the outside, you see the hydrogen burning, and you see the rest of the shells there. But the one thing that is really interesting is you have this inert iron nickel core. Okay, beyond that, we could never go beyond that with fusion because you need more energy to fuse iron into anything than you get out, and that's something that we can't have, right? So the last thing that actually happens is we get a silicon burning. And believe it or not, and this is something that's really interesting, that silicon burning phase is the last phase before the star goes boom. And that lasts for 1 day. 1 day. So if your star starts burning or fusing silicon, you better have an escape plan because it's gone within a day. Isn't that cool?
Does that mean we only have a day to see it if our telescope is looking at it?
Yeah. If it was doing it, well, we would have to know that was happening.
Right.
But that's in the core. And in this image, okay, the entire core of a more massive star is about the size of the Earth. So the whole Earth would be this size here that you see on the screen for that circular shape there. So, but that's neat. But that onion skin thing is really interesting because, in that final moment, that outward radiation ceases. and the star core collapses, and that collapse occurs in just a quarter of a second. That's fast, you know. And it when it collapses, now you got the core collapsing, and now the outside layers are starting to come in, but the core collapses against an inner immovable object, the iron core. So that bounces back off at high speed and bounces back out and directly impacts the stuff falling in from the outside. And that shreds the star into just pieces and just gaseous tendrils, right? I mean, it just destroys the star. And one of the ways to see that, right? And I'll just show you some of this now. This is one of those filaments from a supernova. This is called the Veil Nebula. Okay, this is one side of it. All right, but I want to show you the entire nebula. This is an image we did in SkyTour live stream. This is a composite of several images. That's why it's got this dark squares. You remember this, Daryl? We took this, I think you were in the stream that night.
Oh, yeah.
Yeah.
Just gorgeous.
Yeah. So this is the western veil on this side. Okay.
The
This is
witch's broom.
Yeah, that's right. The witch's broom. That's right. It looks like the witch's broom. Yeah. And then this is the eastern veil on this side. And whenever we look at this, Daryl likes to say, well, that looks like sort of a face, with a nose and a mouth. It does. And you can even see like an eye. Pareidolia works very well, doesn't it?
Mm-hmm.
Yeah.
Yeah. But the interesting thing is now, where's the remnant? Where's the thing that created this? Believe it or not, we kind of know where it is, but we really haven't found it. We have what's called Cygnus X5. It's an X-ray source sort of near the center, and we think that might be it. Now, you look at this. This is 3 full moons across. Okay? 3 full moons across. And it's 8,000 years old or so. In other words, it exploded around 8,000 years ago. And there's estimates of 1,500 to 2,500 light years from the planet, from us. But man, look at those colors. Look at those colors.
Just gorgeous. Very vibrant. Now, did you change a lot of those colors, or are those natural?
No, these are the natural colors. These are the natural colors. So let me just do this and then do like this. Okay, so here's the central veil, the central part of this. Look at the convolutions in there. And Daryl, you're fond of, I think, of looking at these really, really tight tendrils.
Oh, yeah.
And when you talked about this, I wanted to bring it up. These tight tendrils here and these other lines, they look like these filaments. It's a very complicated interstellar medium out there. And what that means is when we look at the interstellar medium, there's a lot of stuff out here. It's not empty space. The interstellar medium is full of dust. It's full of gas. It's full of other things. And all of it is moving. It's not just sitting there. It's moving in a particular direction, for whatever reason, because there's nothing to stop it. So when this supernova went off, it started expanding. And as it expands, and by the way, 600,000 kilometers an hour is how fast it's expanding. 600,000 kilometers per hour.
Is that all? Okay.
That's all.
Mm-hmm.
But it's hitting this stuff as it expands. As it expands, it's hitting this stuff. There's other dark nebula out here, dark dust. And when it strikes that dust, it's being slowed down, and it creates what's called a shock front. And that shock front, which Daryl's mentioned too on our streams, that shock front is something that will be very hot, and it raises the temperature of the gas by millions of degrees.
Wow.
And thus the atoms become nuclei, and they're ionized when the electrons leave the atom. And that ionization is followed by a process called recombination, where the electrons bounced off an atom. That's called ionization. And that's because they absorb a lot of this energy that is being generated by these collisions out there. And then the electron falls back into the atom as it bounces around, hits other things, and then falls back into the atom. When it falls back into the atom, it gives off light. And in the case of oxygen, that light is greenish blue, like you see here. In the case of hydrogen, that light is a soft red, which we call hydrogen alpha, and it's just beautiful. So this is an example of a core collapse supernova remnant. This is what you can expect. And if you think about it, this is a process that populates the universe with all new building materials. Isn't that cool?
Very cool.
Yeah.
Could we zoom back in on that for a second?
Where to?
Oh, up in the middle section of the nebula there toward the top.
Up here?
Some of the really thin lines, the filaments.
Yeah, let me grab those. That's like right here.
The thinnest lines we can see there are like a billion or several billion miles across.
Wow.
I think they compared them to the size of the orbit of Pluto around the sun.
That's right. That was a very good point, Daryl. Thank you. I forgot about that. Yeah. So, and this is for an object that's 1,500 to 2,000 light years away from us. You know, so those tiniest of tendrils are going to be that size, and obviously, all of these stars are just field stars. This is happening. This all is because of one singular star. One singular star that
It must
blew
have
up.
been big. It must have been huge.
Yeah. Well,
Do you
not
think
necessarily.
or not?
It doesn't necessarily have to be. Maybe 8 masses of the sun, maybe 10. And the thing is, you have to understand, and you do, I think, that this is just one supernova of billions that have occurred. When you look at the galaxy, we see all those dark nebula. When we saw the dark nebula earlier that I was showing you, every nebula has this dark knotty nebula in them. And these dark dust lanes, these dark nebula, these come from somewhere. Well, they come from this. They come from the supernova. They come from planetary nebulae. They come from red giant stars that get so large that in their outer environments, they actually make dusty particles that sort of slough off, and that's something that happens in the universe quite a lot, which is obviously true because we see dust in most everywhere we look. And for me, as an astronomer, dust to me is the most enjoyable, most interesting part of the universe. So that's just me. I mean, I just think that. Now, when we talked about the 1A supernova, one of the things I wanted to show you is this sequence of events here. This is a galaxy called NGC 4647. Not this one. That's Messier 60, I believe. Right, Daryl? Is that 60? Thank you. And this is 4647. And in 4647, we saw this blue object that appeared in the galaxy. A new object, but look at the size of the galaxy. Now, the size of the blob just indicates the intensity of the light coming from this, because the blobs will bloat. This is not the actual size by any stretch. It's just a tiny point of light, but it's so bright that it makes that size blob on the sensor of the camera. This is a light coming from this galaxy that is brighter than the entire galaxy. And this is a supernova in a distant galaxy. I don't remember how far 4647 is away, Daryl. Was it like 40 million light years?
Say again, please.
Was it 55 million light years?
Yeah, it's 50 or 60 million light years away. It's in the Virgo cluster. We first saw this back early April, I want to say, and we watched it over time. It has been a popular request. Unfortunately, Virgo is starting to go away now, and probably by the time we get to look at Virgo again, it's going to be next spring, and the supernova will have died away by then.
Yeah,
it'll be interesting to look at, to follow up on.
This is a 3-month sequence that we did. This is the supernova in April, like you mentioned, Daryl. And then this next shot is the same supernova seen a month later.
Oh, wow.
Look at how red it is now.
Red, yes.
Okay. Now, remember what I showed you when we looked at this diagram? Hottest and bluest is going to be like the O-type star, right? and then M is the coolest. Well, think of it as that's just a temperature scale. All right. So if a star is hot and blue, it means it's a certain temperature. If a star is redder, it means it's a cooler temperature. What we're witnessing here is the supernova getting cooler. As it expands out into the interstellar medium, it's cooling off. So it goes from hot and blue to cooler and red. You see?
Yeah,
Isn't that cool?
it is. It's contrary, though. I would think cooler, like ice, would be blue.
I know that's a common issue that
Mhm.
you have to overcome in astronomy. For people starting out, is that blue means hot. Now, if you want to see it properly, you look at a flame, and the blue part of the flame is hottest, right? And the orange part of the flame is coolest.
That makes sense.
Like
Right.
on a welder's torch.
Exactly. Very good call. On the welder's torch. Yep.
Yep. The
So
hottest part is at the very tip of the blue part of the flame.
Yep. And you don't want to put your hand in there.
Oh no.
So that's that. So this is the May version. Okay. May 29th, as a matter of fact. And then on June 22nd, this is the image we saw. All right. And you can see that now it's actually a little bit fainter, but depending on how the exposure was taken, it can look a little bit different. It depends on the quality of night as well. But from May to June, it didn't really change that much. But if we were to see it now, I'm quite certain that it would be a lot dimmer than this.
Yeah. And when the Crab Nebula supernova happened, it started out very bright, blue-white. It was so bright it was visible in the daytime sky.
Yep. Yeah.
And it faded, turned red, and faded away over time. And when Betelgeuse blows, it'll start out so bright, it'll be bright in the daytime. It'll eventually start to cool off and turn reddish, and maybe not visible in the daytime sky anymore, but it'll be as bright as a full moon in the nighttime sky. And it'll turn redder and redder, and it'll eventually fade away.
That's right.
And hopefully what we'll see then is a brand new nebula up where Betelgeuse used to be.
I'd like to see that.
That'd be cool.
Yeah. Now, here is the Crab Nebula, right? And the Crab Nebula was seen. We shot here. And in the middle there is that object known as the Crab Pulsar. This is a neutron star that has hot spots on it, like a lighthouse beacon. And as it spins around, it flashes the Earth. Just by chance, the lighthouse beacon, swings around and we can see it. Okay. So because it does that, we actually can calculate how fast this pulsar is spinning. And for a star like this size, all right, and I'll give you an example. This is the size relative to Chicago of a neutron star. Okay.
Great visual. Good.
Right. That's how big a neutron star is compared to Chicago. Okay. For that size, this star is spinning around 33 times per second. Now, you got to think these stars are held together so strongly that they aren't flying apart. And guess what? That's not even the fastest speed. The fastest speed for a star, again, this size, right, rotating, is over 700 times per second. Now, you got to imagine that that's a really, really strong, cohesive star. Because you know what it's like. If you take a CD and you spin it faster and faster and faster, it reaches a material limit where all of a sudden it'll fly apart, right? Well, not so for a neutron star. So far, we haven't seen any neutron stars that have spun themselves to death.
If it ever did spin itself apart, it would decompress and it would blow itself to smithereens.
Oh, absolutely. Yeah.
Yeah.
Because
the only thing keeping it together is its gravitational pressure.
Mm-hmm.
And if it ever broke, it would you would have a titanic explosion.
Yeah. Maybe that's a kilonova. Right?
A super kilonova.
It's funny. Kilonova sounds smaller than a supernova, but it's actually bigger.
And then the biggest one's a hypernova.
Yep.
So I don't know how many hypernovas. I think there's only one hypernova that's been seen, as far as I remember, and I can't tell you where it was. If I knew where it was, it would have been it would have been in the northern hemisphere. It's probably somewhere in the southern hemisphere.
I have a question. How can they count how many times that rotates a second?
Oh, okay. The pulsar, as I mentioned, it has this lighthouse beacon. It goes, it's going around, and they can actually, literally, visually, you can actually see it. Actually, not visually, but in the radio spectrum, you can actually see the flashes occur and time it directly. All right. So what they do is they slow it down. They capture the light, and then they slow it down, really, really slow. And they could actually watch it doing this. You could actually see it doing this, flashing. And then from that, they can calculate the speed of rotation.
That's very cool.
Now, the problem I have with it is, what if there's two hotspots? Then it might only be spinning 15 times per second. All right, because they're getting the first one, and then the second one hits, and then you see the first one again. But because you see 1, 2, 1, 2. Well, you'll think that's 33 times per second. It might be only 15 times per second. But maybe there's 3 hotspots or 4 hotspots.
I thought there could only be one on.
I always thought there'd be 2, like
north and south.
Okay, poles.
They're at the magnetic poles, yeah.
Yes.
Yeah.
Folks, we're coming up on a break.
Okay. We are, aren't we? All right, good. Well, you know what? Thank you, Daryl.
Yeah.
We will be back right after these words.
DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
The experiencer phenomenon is happening for a lot of people just like you all over the world. People are telling very similar stories about personal encounters with non-human intelligence. The Mutual UFO Network has research, resources, and support to help you make sense of what is happening. Our experiencer community is growing every day. Join MUFON, find your friends.
Hi, I'm Austin Butler from Baz Luhrmann's new film, Elvis.
Tomorrow, all of America will be talking about Elvis Presley.
As a blood donor himself, Elvis shared the gift of life with patients in need and asked others to do the same. We're encouraging you to give blood this summer. Please visit redcrossblood.org/ElvisMovie today to learn more.
You're listening to the KGRA Digital Broadcasting Network. We provide unparalleled coverage of trending news in the world of ufology, cryptozoology, and paranormal phenomenon. Whether you're watching our video live stream or listening to one of our audio programs, you are getting the best from world-renowned researchers and hosts, guiding you through topics the mainstream won't touch. Miss one of your favorite programs? No problem. Head over to the members area at kgradb.com for access to our massive library of award-winning content. Make contact, stay connected, only at kgradb.com.
Hey, welcome back to Skyter Radio. I want to Thank you guys for joining us tonight. I had one more thing to show you before we go over to Daryl and have him take us on a deep dive. I wanted to show you something about that Crab Nebula we just talked about. You know, it's expanding in space, and there have been some tremendous videos and so forth created. I just want to play a real quick one for you to show you what this looks like in the real world. Now, it's expanding at a rate that's, oh gosh, uh, okay, it's spinning at 33 times per second as debris is pulling out. It takes years for the expansion to show up, and it's expanding outward at about 1,500 kilometers per second, which is just under 1,000 miles per second. That's expanding, but it takes so much time for that to be seen. But check this out. This is the Crab Nebula you're seeing right here, and this is 1999 from 1999 and 2012 images that were taken. All right, so watch now as the expansion takes place. It's a repeating loop. All right, look at this. So there's 1999 and there's 2012. Do you see the difference?
Wow, that's cool. It's changed colors too.
I think the colors are due to the fact that a different set of instruments recorded the colors.
Okay.
All right. But you're right. If you notice how at the end, like down here, you see these blue tendrils, which are now out here. And there's actually a star out to the upper right here, just out of the shot. And you actually see the star moving against the background because in the time that in between these exposures, the star has its own motion through space, and you actually see the star moving against the stars a little bit. It's really cool.
It's the breathing Crab Nebula.
Yeah, it's the breathing Crab Nebula. Yeah, and there's another one actually with a 2021 shot in it as well, and it's just a little bit more. So it's 3 shots. But isn't that amazing?
Beautiful.
Yeah, it's pretty cool. But anyway, so that's the beauty of the Crab Nebula, to show you that it's a dynamic universe. It takes time to see it, because we're not able to live long enough to be able to see these vast changes. But luckily, we have guys like Daryl who will take us through a deep dive and show us all about the universe in just a few minutes.
Wonderful.
Right, Daryl?
I hope so, yeah.
Yeah, we will. You always do. Well, take it away. I can't wait to see what you got.
Okay. Doodah.
Da, 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 da.
Okay, there we go.
Ta-da.
This is the sky tonight, and I'm going to back up an hour. You see, this is before sunset. In fact, I'll back up 2 hours. Note that Venus is moving this way, about to pass behind the far side of the sun. And when that happens, Venus will be over here, and it will then, it's called a superior conjunction when it passes behind the sun, and Venus will be back in the evening sky. Now, simultaneously, sorry, one more time. Here it is, 7 o'clock, and the sun's about to set already. The sun is actually setting at about 7:35 at night here now. So the sun just set, and Mercury is very low in the west still. You would need optical aid to see it. If you could look at it with a telescope, you'd see that it's presently a very small, very thin crescent as it is getting closer and closer to the sun. Mercury is moving this way, and that little crescent is getting skinnier night by night. If you do look, wait for the sun to go down so you don't blind yourself, please. But you can actually see that little bitty crescent of Mercury, and Mercury will be gone to the morning sky before Venus returns to the evening sky. They're going to try to kind of change places. And when Mercury passes on our side of the sun, between us and the sun, that's called an inferior conjunction. So Venus is about to pull a superior conjunction, and Mercury is about to pull an inferior conjunction. And they'll hand off, and Venus will be back in the morning sky for months and months to come. And a very young moon. The moon is just past noon now. You may not even be able to see it yet. If you can, it'll be the least little fingernail paring of a moon, but it's going to go farther east and get higher and fatter every night now for the next couple of weeks. One more hour, and the sun is gone, and you see Leo is pretty much lost in the sunset now, and Virgo's following it. The supernova NGC 4647 is right up in this part of the sky, and so Virgo is pretty much gone now too. We might get one last look at it, but it's low, and the seeing will be very poor over there. And when Virgo goes, here comes Libra behind. Libra is not far behind. I'm going to switch to the south now, and 8 o'clock at night. It's not dark yet, so we'll give it another hour. There's 9 o'clock. And you see Scorpius is getting really low already. Scorpius is well west of the meridian. Sagittarius is actually transiting the meridian by 9 o'clock at night now, and the stars of summer are going away. They seem to do that. But there's going to be a neat thing kind of happening here in the coming weeks, because the days are getting shorter as we approach the autumn equinox. The sun's going to set earlier and earlier each night, and the stars are going to seem to almost stand still for a while. So they move really fast in winter, because all the neat stuff here along the plane of the ecliptic, because they're so far south this time of year, they tend to go quick, but they're sort of simultaneously going to be almost standing still in the sky for a while as the days get shorter. But they will inevitably go away. And you can see Scorpius is pretty much gone by 11 o'clock at night now. And Sagittarius isn't far behind. But as we see the teapot there, and as it gets later in the evening, the teapot will appear to tip over to the right, and the Milky Way becomes the steam coming out the spout of the teapot, like it's pouring the tea this time of year. And it's pretty cool to watch if you go out and see that this time of year later at night. And where we've been lately, we've been exploring all this here: Scorpius, Sagittarius, Ophiuchus, that comet we've been watching, C2017 K2 Pan-STARRS. It was up here in Ophiuchus, and now it has moved down by this star called Crab, which is, I think it's the left elbow of the scorpions, of the scorpion. And it's going to continue moving down this way. So you see it's moved like that over time, and we're probably going to lose it to the morning, to the southern sky here pretty soon, but we've still got some pretty cool looks at it recently.
I can show some if you want me to show a picture of it, Daryl.
Sure.
Yes, please.
Okay. This is K2 Pan-STARRS as we saw it. I think about 4 or 5 weeks ago. Every one of these lines is a satellite going through, which is really awful, but that's what happens, right? So we see these, but there it is. You see that beautiful green. That green is molecular carbon and cyanogen, carbon and a nitrogen atom, cyanide by any other name. And you see the long dust tail behind it. And you can't really see the ion tail. Every comet has 2 tails, right? The interaction with the surface of the comet creates ions which stream behind it directly away from the sun. And the dust tail is just its path through space littered with debris of the comet. If the Earth passes through those at some point, we get a meteor shower, because that's what that is. So this is the comet that Daryl was just talking about.
Yep.
Ta-da. And back
it's
to you.
been really cool, and the comets tend to walk over time, night to night. So a while back, it was up here in southern Ophiuchus. It has now moved down towards to the right, to the west of that star Crab, and it's going to keep going that way, and we're going to lose it to the southern sky here directly. That plus the whole constellation Scorpius was pretty much gone by 11 o'clock now. Anyway,
Yeah.
but as we rotate around, revolve around the sun over the course of the year, well, here come the stars of fall now. Saturn is well up by 10 o'clock at night. We tried to look at it the other night, but Mark's Wide Field Telescope doesn't show the planet too well. We could see it, but not much detail.
Yeah.
And hey, look, by 10 o'clock at night now, Jupiter is well up also. We'll have to wait a little while till Jupiter comes in the field of view. Probably at this time right now, the roof of Mark's Observatory is cutting it off. But we'll give it another hour or two. And 1 o'clock in the morning is true midnight, taking away daylight savings time. And Jupiter is going to be at opposition. Saturn was at opposition early this month. Jupiter is going to be at opposition in September when it crosses the meridian at local midnight. That means it culminates. That means it moves from the eastern morning sky to the western evening sky. And after opposition, Jupiter will be an evening object along with Saturn. And it will, when it crosses the meridian at midnight, it will be at opposition, and it'll be in the sky all night long. It'll rise at sunset and set at sunrise. And we're going to see Jupiter on its way around. And we'll keep on going around the sun. And hey, by 11 o'clock at night now, the Pleiades are up. Mars is almost up. And when we looked at the Helix Nebula the other night, Helix is right about here, right under Aquarius. And actually, the satellite, the asteroid Vesta is there also. So we have all the fall objects coming up now that we'll be looking at. And as Sagittarius, Scorpius go away, we'll be able to see Scutum and Aquila the Eagle for a while. Cygnus, you see, is Deneb there is transiting the meridian by 11 o'clock at night now. It is well on its way.
Yeah.
And there's the North American Nebula and the Pelican Nebula. And when Mark shows us the Veil, it's right about there.
Yeah.
And the dumbbell is there in Vulpecula the Fox, Little Fox. And we'll keep on moving up as, whoops, didn't mean to do that.
Well, actually, Daryl, while
yeah.
we're still in that region, I have a much closer view of the Helix that I can show folks from that smaller one. So the Helix is a planetary nebula. This is what it looks like up close. That star in the middle there, we'll even go closer here. That star in the middle, that is actually a white dwarf. Notice the color. It's blue.
Blue.
Right. And we talked about blue, right? Remember this diagram? Okay.
So it's hot.
Right. Yeah, that's right. This diagram, actually. Yeah, blue hot. So there, that's that blue end of the diagram is where the star that's really hot is. If you notice underneath this main line, you see white dwarfs right there.
Yep.
Okay. To the left side, the bluer they are, the hotter they are. And that's what we're looking at here. We're looking at a blue hot white dwarf, which is why you see that right there in the middle. And you see this radial pattern moving out from the center of material streaming away. And we're seeing this in 2D. So we're not seeing it in 3D. In 3D, it looked very different. It could be like a barrel. It could be a much more complex shape. We see stuff out here. This hydrogen gas that was expelled earlier in its history, likely. There's another one down here. This is just gorgeous. And again, it's expanding into a medium that's not empty. It's expanding into a medium that has stuff in it. So the outside shape isn't a perfect sphere. Like here, look, it's hitting something which is causing it to slow down at this end, and it's getting compressed against this edge, you know. Same here and up here. So there's a lot going on, but really cool stuff. So that's a planetary, so named because in a small telescope, they look like a planet.
Yep. This is the. You can put that back up for a second if you
sure,
like.
sure.
This is the closest nebula to Earth. I forget how close. It's a few hundred light years away. It is the closest planetary nebula for sure. It is quite large in the sky from our point of view, but partly because it's so close and it's so big, it's very dim. You can't see it naked eye. I've only seen this once in a telescope. That was in a great big telescope with a special filter on it. But here you see the wonders of digital astrophotography. And when you look at that white dwarf in the center, as Mark likes to say, it's about the size of the Earth, yet we can still see it hundreds of light years away because it is so darn bright and it is so hot that it's radiating mostly in the ultraviolet.
That's right.
And that ultraviolet light is what is exciting the gases to make them emit like that.
That's right. And the greenish blue is oxygen that used to be in the star's envelope. And this is, we talked about supernovae, right? We talked about, the white dwarf supernova and stuff like that. Well, this is a singular star that went into a red giant phase, and then as it started to pulsate. As it ran out of hydrogen, it would start to shrink, the core would get hotter, and then helium would start to fuse, and it would use that, and then it would shrink again. But each time it pulsates, it gets bigger and smaller. And when it gets bigger and smaller, what it does is it actually starts to slough off those outer layers, because it gets so big that those outer layers are, again, beyond that Roche lobe we talked about before, where that material is no longer really bound by the star anymore, and it can just sort of float away. And so that floating away process is what caused all this that you see here over time through pulsating. And so that's what happened. Then, of course, the white dwarf did its job and ionized all that gas because it's so dang hot. And with the hydrogen glows red, the oxygen glows bluish green. Other elements, there's many, many, many other elements in here as well, not just hydrogen and oxygen. Okay. But it was all the stuff made in the star when it was made.
So is it bumping into dark matter or dust? Is that what is?
Yes. It's bumping into dark dust out there. It's bumping into other neutral hydrogen, that's cold hydrogen gas, making it hot. And as it does so, the speeds at which this is moving out is not the speed at which a supernova moves out. This is a slow process we see here. This is much slower. The high speed process is when you get that bam, that big explosion from a supernova. This is a slow death, slow process. This is how it's going to happen to us. Yay!
Yeah. And when you look at this, the strength of the ultraviolet is only enough to make the gas emit for a certain distance, and that's pretty similar for all planetary nebula, if I remember correctly.
That's
and it's
correct.
Like that lobe you see out there to the upper left, which is barely illuminated. Well, there's surely more going on farther out to the upper left and to the lower right, and all around the nebula, I suppose. But it's far enough away from the star that it's no longer emitting a light. So we can barely see that outer layer at the upper left, and there's even more farther out that we probably can't see at all anymore. And this is the ultimate fate of our sun. It's of a size that when it gets old and goes through its red giant phase, it's ultimately going to become a planetary nebula like this.
Yep. And I'm sure that from some distant star, some other civilization is going to say, and this is the Sol Nebula, the nebula around the star named Sol. Okay. That's actually our sun's name. Of course, nobody else would know that. And it's spelled S-O-L, Sol.
Well, it's a big universe. Maybe they would call it Sol. You never know.
That's true. That's right.
Could happen.
Yeah. All right, Daryl. So go right ahead.
Okay. Let's see. There you go. All righty. So we are now, again, the Helix is right in this area, close to the asteroid Vesta. Vesta is something else we should look at, Mark. We might be able to see it moving.
Okay.
But we have traveled up along the Milky Way, and we've been spending a lot of time in Cygnus lately. And I bet you dollars to donuts, Mark has an image of the Gamma Cygni Nebula. There is Alberio, Mark showed us earlier, the head of the swan, that pretty double star.
Mm-hmm.
And then you get up here in the middle, that star's name is Satyr. It makes the Satyr means breast or chest. That's the breast of the swan. And then on up to Deneb is the tail of the swan. Deneb means tail. The Veil is right here. And Mark recently did some really amazing imaging of the Gamma Cygni Nebula. I bet you'd like to show that to the people.
I do have it. And keep in mind that our size of our telescope field is it's it's 4 full moons across, all right, and 3 full moons tall. Okay, and keeping that in mind, this is what I got. This is a composite. This is one frame. This is another. This is another. This is another. Another. And another. Okay, and so I did 9 total frames, and I combined them, and then processed them today.
You missed a spot.
I did indeed. That was my mistake. I was trying to rush the weather because I did this last night. Okay, I did a private stream for myself just to quickly do this because I got a little moment of clarity.
For clouds.
Yeah, the clouds were there, but again, it's the monsoon season down in the Arizona desert. And
is that the star Satyr there, left to center?
Right there, yep.
Okay. Then you can even see the Crescent Nebula down to the lower right.
Yeah, I actually did this composite to show the Crescent Nebula down here and its relation to the Gamma Cygni Nebula, which is right here. And I'm planning on filling this in tonight if we can get going. I'd like to do that, but it depends on the weather. But see, this nebula and this nebula are formed by 2 different processes. These have all these knots of dark nebula in here, and let's actually let's go in here and back out for just a bit, and let me bring us out. So you see all these dark nebulae in here, and we also have reflection nebulae, these beautiful blue, subtle nebulas in here that are dark dust that's scattering the blue light of the stars. Where there are some here, there's no stars to do it, so it looks just black against the red background, right? But these are scattering light. And then as we move down, right, we can see there's Satyr right there, the star Satyr. Actually, this is not the one that I want. I think this is the one we want right here. So I'll let that come in. There we go. Okay. This is the one that was processed more correctly.
Yeah, very deep black there.
Yes, really nice view. And let me take us out a little bit. And you see, everywhere you look, there's a little picture, like this little beautiful picture here. This little curly Q of dark nebula right there. A little one right here sticking up with a little, like a C shape. And then behind it is a red hydrogen emission nebula, right? And then we get to the complex parts of the nebula. Look at this.
Oh, that's so pretty.
Isn't that gorgeous? And the nice thing is you can zoom in and zoom in and zoom in. You can go right into it, you know. And that's what's nice about our sensor that we're using for our telescope. We can actually do a lot of zooming, and it supports that. And then here is this other nebula here, the Crescent. Now, that star right there is responsible for the Crescent. And what happened is this star, okay, is a very special star.
Wolf-Rayet star, isn't it?
Yeah, it's a WR star, Wolf-Rayet, very, very hot. And the star, for whatever reason, had some tumultuous episode where it blows off its outer layers. All the hydrogen and some of the oxygen gets blown off. And primarily, you see this hydrogen envelope that's now, of course, ionized by this remainder of the hot star, the core. And this star is heading towards supernova fandom. at some point. It will make a beautiful supernova at some point. We see Thor's helmet in the winter. Thor's helmet looks beautiful green. Thor's helmet is also a Wolf-Rayet star site as well, which we'll see again. Go ahead, Tara. I think you had something to say.
No, I was just saying it looks like a potato to me.
It does. It looks like a potato.
Mm-hmm.
Yeah, it does. But the crescent, of course, is from the C shape here, right? So that's what they say.
Fry them, smash them, stick them in a stew.
No matter what, it's all good for you.
That's a prime supernova candidate, is it not?
It is.
So you're like sometime, probably not in our lifetimes, unfortunately, but you're going to see that one go supernova, and that's going to light this area up like you wouldn't believe, I bet.
It will. And then it'll leave a remnant of its own to go along with the Southern Nebula. Yeah. And then what would a image be without a little satellite trail going through it? We have a little satellite trail over time, and one thing you'll notice is that it's sort of has little bright spots on it. And that's indicative of the fact that this is probably debris, not a satellite. It's a rocket body that's probably tumbling, and it glints in the light a little bit, and you can see it every so often. It's pretty regular. It happens at regular intervals. That's what you see. Oh. Yeah, that's the Gamma Cygni Nebula complex as seen from Skytour Livestream, and we took this just yesterday. So back to you, Daryl.
Okay. We're back. So that's all Cygnus, and there in the middle, Satyr. Whoops. And then here is Deneb, and we're spending time up here too, North American and Pelican Nebulas. Really cool. And as the seasons change, well, golly, looky there. Pegasus is coming up by 11:30 at night, well up, getting close to the meridian, actually. But here's Pegasus, and oh, darn it, settle down. Andromeda is up. There's M31 Galaxy in Andromeda that we have to look forward to. That's the great big galaxy. Cepheus and Cassiopeia. This is all the cool stuff here. The Iris Nebula and the Cave Nebula, and getting over into Cassiopeia and Perseus. And here come the stars of winter. The Pleiades are up by 11:30, and Capella is rising in the northeast by then. And the stars of winter are on their way. That's pretty much all I have.
Okay, well, thank you very much, Daryl. That's wonderful.
Sure. Thank you. That was awesome.
Okay. And as we look at what he was talking about, he said Pegasus was rising, and Pegasus has right next to it Alpheratz, which is a star that we use as to define where Andromeda starts, and when you follow up from there, you can reach this guy right here. This is the Andromeda Galaxy. The Andromeda Galaxy is stunning. We took this, of course, in the observatory. All of our exposures, the images we take are only they're only like 20 seconds long, because we don't need to take longer than that with those beautiful skies out there. But I wanted to show you something with the Andromeda Galaxy that we'll be able to see dynamically when we look at it live. Again, this is just about what the people saw when we did it live. Notice these blue spots in here. Daryl has talked about these before. We see them up here as well. These are areas in the Andromeda Galaxy where stars are forming at a prodigious rate. Lots of star formation going on. And those are in the spiral arms. And these are very hot blue stars. And by now, we're talking about O-type stars and B-type stars. So these are OB associations in all likelihood out there. And these are extremely hot locations where life could not exist at this point, but they were once hot stars here too, and this has changed over time as the stars have changed. They've evolved, they've blown up, allowed more massive or less massive stars to form. Then once that happens, in these more quiescent areas, this is where the seat of life is, in these stars here. These are the hot young upstarts. Okay, these probably wouldn't have a lot of life going on in this region, but we'd certainly have planets for sure, no doubt.
Yep. And when those OB associations supernova, they reseed the galaxy with all those dark clouds. It contains
like these.
the higher numbered elements.
Yeah, like
and
these
that's
right
where
here,
the
yeah.
future stars and planets and people come from.
That's correct. And the beings, like other beings. And then inside the galaxies, even though they're, in this case, 2 million light years away, you're seeing the Andromeda Galaxy as it was 2 million years ago, we see our own, just like we have here, we see these hydrogen stellar nurseries. These, we call them H2 regions. Those are regions where we're watching stars form as well. There's many of them in this galaxy. And right next to this galaxy is another galaxy that is really interesting, again, for the same type of reason. And I'm going to show that here on the same night we did this one. Okay, this is Messier 33. And this galaxy looks messy compared to the Andromeda Galaxy. And it's sort of messy because its spiral arms are not as tightly wound. All right. And, but you'll notice that it's also got a lot of blue arcs of stars. These are very, very large associations of stars. But look at all the red spots. Look at this one.
It looks like speckles of gold.
Doesn't it?
Freckles.
Yeah. Yeah. Look at this bright bluish green object here. And bright blue-green object here and here. There's lots of them. You know what those are?
Emeralds.
Supernovae remnant. These are supernovas in another galaxy.
Wow.
Right? And then you can see in the spiral arms, you got knots of dust in here. This dust, again, as Daryl was pointing out, is the seed of life, right? The foundational building blocks of other stars and planets are made in this dark dust. All right? We've talked about it before. I won't go into it tonight, but basically the dust has ice on it. The ice attracts methanol, formaldehyde, CO2 ice, water ice, and other types of ices. And that stuff becomes the foundational elements that form other stars and, more importantly, planets. So it's amazing to see the universe unfold before us here, and you learn all about how this stuff happens. This galaxy is actually very close to Andromeda in the sky, and it's just a little further, just over. I think Andromeda is 2.2 million light years away. This is like 2.4. Is that right, Daryl? Do you remember?
Something like that. 2.5, 2.5.
Yeah. So again, we're seeing it as it was 2 million years ago. But look at all these hydrogen regions in here. It's full of them, and every one of those hydrogen regions in there are making stars. That's why you see them. Stars have already formed in there. So that's beautiful. That's what we got going on in our galaxy. You know, I kind of like our galaxy. I don't think I'll change that for the world, huh? What do you think, Tara?
I love our galaxy, and it always is interesting to see when we're looking at things in our galaxy and outside of our galaxy. So I always have to think about that. So
that's actually a very good point, because all the stars we saw in that image were actually stars that were inside of our galaxy, and we're looking through them to see the other galaxy way out here in the distance, you know. So that's what's going on.
Yeah.
The galaxies are out here, and we're looking at the stars that are in our galaxy. So interesting stuff. So I want to actually now, Tara, turn it over to you to ask us some really cool questions. You must have some.
Well, I probably have some. Well, hopefully they're cool. Okay, well, I have a question about light.
Okay, this is Tara's Cosmos, by the way.
Okay, so what is the speed of light measured in relation to? I mean, is there an opposite of the speed of light? Is there a fixed rate of rest? I mean, how?
Oh, that's interesting.
It's just a silly question, but curiously, is
No,
it, if you can
it's
go
not
back and
silly.
so there you go.
It's not a silly question. We all know the speed of light as measured in space and looking at light echoes and so forth. 186,282 miles per second. That's 7 times around the Earth in a second, basically. That's pretty fast. If you want to have an interstellar spacecraft, however, that's not fast enough by far. You need to have something much faster or something that can sidestep that. So the speed of light does vary, but it only gets slower. It doesn't go faster. The speed of light in a vacuum is what we call the speed limit of the universe, but only in our X, Y, and Z moving through time, our 4 dimensions. Okay, it's a constraint by our physical universe, and nothing can go faster than the speed of light, technically. All right, but the speed of light in water, the speed of light through a translucent object is different. All right, and it's just a little bit slower, but it's not faster.
Yep. And light travels at the speed of light because it has to. It has no choice. Light, by its nature, photons travel at the speed of light. And we're opening a great big can of worms here. Gets into relativity and everything.
Yeah, it does.
Yeah. If you were to travel to Proxima Centauri, say, at the speed of light, it's 4.2 light years away. It's the star closest to the sun. If you were riding in a spaceship going at the speed of light, or if you were just a photon traveling as you normally do, no time would pass. It would be instant. Now, if you were watching you inside that spaceship or on that photon, no time would pass. Just bang, all of a sudden you're at Proxima Centauri. This is the time dilation thing, and you're getting into relativity here. That the faster you're moving in your reference frames and stuff, the faster you're moving, the slower time passes for you inside that reference frame. But if you're, say, standing on a planet Earth and you watch that spaceship move away, it's going to still take 4.2 light years for that spaceship or that photon to get to Proxima Centauri. And that's depending on your point of view, and that's what relativity is.
Right. It's all a matter of perspective, and that's an interesting fact. We call that a reference frame. The reference frame is the observational frame of reference within which you are located. But if you see someone else traveling in that spaceship, say you go by the Earth at the speed of light, in your spaceship, you're moving around normally, and it seems normal to you, and you're waving as you go by the Earth. Boom, you're gone. And you say, well, I hope they saw me wave. But on Earth, if they looked at you in the spaceship traveling by at the speed of light, here's what they'd see. They wouldn't see you moving. Because from their perspective, you're not moving. Time is stopped for you from that reference frame. It's a weird thing that's part of the time dilation thing. So,
aren't you glad you asked that question?
I know.
I am. Well, it's kind of an interesting question. Do we ever reference anything? Like we always refer things to the speed of light. Do we ever reference anything to a fixed rate of rest?
Well, okay, that's another really good question. Thank you for making that point. Everything in the universe is moving, right? And you might imagine that when someone says, how fast is the Earth moving through space? You have to say relative to what?
Right.
Yeah.
The sun, to a particle of interstellar dust a light year away. But that particle is moving too. So there is a standard of rest that is in the universe that's used just to kind of form a reference. but it's not. I just think I look at it as the universe. Everything is moving, so everything is relative to something else. So if someone says, "How fast is that moving?" The next question always is relative to what? Because we don't. We have to clarify, because you can't just say the Earth is moving at this speed. Okay, how fast is the sun going around the galaxy? Okay, that we can answer. How fast is the Earth going around the sun? That we can answer. How fast is the Earth moving through the universe? Well, that's tougher.
Yep.
See?
That's cool.
When the Webb telescope sees those galaxies out at the far red end of what we can see in the observable universe, they're moving at an appreciable fraction of the speed of light relative to us. Or you could conversely say we're moving at a good fraction of the speed of light relative to them. It all depends on your reference frame. I mean, if you stand on the equator, you're going about 1,000 miles an hour as the Earth spins on its axis. If you're standing on the Earth and you look at the sun, you're going about 67,000 miles an hour as we orbit the sun. If you look at us relative to the Virgo cluster, we're going thousands of kilometers a second. And if we look at a galaxy far over on the far side of the universe, like with the Webb, we're going an appreciable fraction of the speed of light.
From its point of view. Yeah.
That's cool.
And then
that's relativity.
And okay, because of the way the universe is expanding, and let me just give you an analogy for the universe expansion. Okay, if you blow up a balloon to about, say, this big, and let's say the balloon blows up to about that big, right? It blows up just about the size of a softball, and you take a Sharpie and put black dots all over it. Now you blow that balloon up. Well, as you blow that balloon up, the black dots farthest from you at the other end of the balloon are moving away from you faster than the black dots near the stem where you're blowing into. Okay, that's kind of a model for how the universe is expanding. It's expanding faster, farther away. See? And that's what we're seeing. And that's the thing that the latest findings showing that the universe is accelerating outward. It means that someone's still blowing up the balloon. Okay. Now, that is why, in part, why dark energy was created, to kind of explain that acceleration. It's a repulsive force that makes everything move faster away from each other. Okay. But as Daryl said, the perspective is very important. From the distant galaxies' point of view, we're the ones with the very high redshifts. That is to say, the high speed of recession, moving away from them at very high speed. But from our point of view, they're the ones moving farther away faster.
Yep. And we don't even feel the wind in our hair.
We don't even feel the wind in our hair. But that's only because there's no wind in space, you see. So again, are you glad you asked that question?
I am.
Will you ask it again?
I'm possibly, sometimes I need to hear it a few times to get it,
Fair enough.
Fair enough. Go ahead, Daryl.
You asked about a reference frame of something absolutely at rest. It's all relative to where you are. You could say we're at the center of the universe, or you could go over to the next galaxy over and call it the center of the universe. We're all, in there, and we're all moving.
Yeah. So that's how that works. All right, Tara, let me hear something else. Give us something else. Try to
okay, so let's
tease
stay
our
on light.
brains.
Okay, here's another strange question. I was kind of thinking of sound waves, but do light waves echo, or can they echo? And if so, what would that look like? Or do they bend, or what does that mean?
Let me see if I can show you a light echo, because I was going to show you a light echo earlier. What is a light echo?
I don't know. Okay. Is it a reflection?
Are you going to do that 808 monostratus or whatever it's called?
I was going to try and do the light echo from R.S. Puppis.
Is that a meditation?
Yeah, right. I'll show you. Okay, this is from the ESA. Let me see if this is the one. Okay. Well, I'll just play a few and make sure. Yes, this is the one. Okay. Okay, now you're going to see a light echo. This is light echoing, meaning as the light moves through dust in a nebula, you actually see it like ripples on a pond. You ready? Okay,
I'm
so
ready.
let's bring
Hold
this
on.
up. There it is.
Okay.
Okay. All right. And now let's watch. Okay, here's the nebula, and here's the
Okay.
dust. All right, now watch as they zoom in. They're going to show. Watch the ripples. Look at that.
Oh,
See those ripples?
looks like water.
It does. That's a light echo. That's what happens when
Oh,
a star pulses and it's pulsating and pushing off just a wave front of light. And then what it does is it actually creates this beautiful wave pattern, just like you see in a pond, and that's the light echo. So I'm glad you mentioned that, because now you see it. Look at that.
that's awesome.
And it's moving at the speed of light. Now, what you're not showing you is the time over which this happens. Depending on the size of this nebula, if this was, say, the distance from, say, the sun to Pluto, if this was like, say, let's say it this way, the sun to Pluto, then this would be a light echo that takes several hours. Okay, but if it's several light years, then it's going to be a light echo that takes a lot longer. Do you see?
That's
But
cool.
there you go.
Is there anything we can do with that technology? Is there a reason to use it?
Not yet.
Yeah, right. Well, remember, light speed is not a very fast speed, and that's part of the problem. Okay, if we want to move faster, get around the universe quicker, light speed right now is out of our reach. All right, because it has ramifications for physical matter trying to move as fast as light. Okay, you become pure energy, and that means that your body gets destroyed as you get converted to pure energy. So, not a good idea. All
No,
right.
thank you.
So you say, oh, well, we'll go 99% the speed of light. Yeah, that'll work. If we can do it, yeah, that'll work. But then it's going to take more than 4 years to get to Proxima Centauri, the nearest star. Okay, because you're not moving at the speed of light, you're moving slightly less. So the speed of light is pretty slow for beings like us to get around. What we need is dimensional travel of some kind. And if string theory is true, then perhaps we'll be able to use some type of string theory propulsion concepts. Like I've been lecturing around the country on this lately, and I won't go into it now, but that could be a whole show in itself, actually, about how a potential alien spacecraft, which could be ours someday, could actually go from, say, here to Alpha Centauri in like a 20-minute time frame or less.
Cool.
Odd as that sounds, but the way it works is we punch out and punch in. We don't go through the intervening space in the universe. We actually move outside of it and then come back into it.
It seems like a long way to go to get outside of it, because it seems like it's huge no matter where you look.
Yeah, that's true.
It's
But
hard
yeah.
to comprehend.
Well, tell us more. Before you do, though, I just have to ask, we'll go over here. Kathy Pernasek in the chat, hi, Kathy, asked about the Big Bang and said, do I think the Big Bang didn't happen? The jury is still out, Kathy, but we're going to examine the James Webb results and come to a decision. And that's the collective we, because I'm not directly involved in any of that particular research. But I'd be interested to see the findings and to see it indicated. I do know this, and I mentioned this to Daryl earlier. Our equations to determine what's happening at the beginning of the universe are not sufficient. They don't work. Okay, that's why when the Big Bang occurred, we have to consider it a singularity, an infinitely small point. But everybody knows, every cosmologist, every astrophysicist, every astronomer knows that that's not at all what it was at the very beginning. It wasn't an infinitely small point. It was a massive, massive object, perhaps the size of the universe itself, for all we know, that did explode. But how that happened is still a mystery to us because our equations, our relativistic equations especially, can't accurately show us how that actually works.
There's some maybe misinformation out there that's come from recent Webb telescope results. Some people are saying that sort of discounts the Big Bang Theory. I think that remains to be seen. They may have to reinterpret, their former theories to account for it. If I remember correctly, they said basically they're seeing spiral galaxies much earlier in the universe than they thought was possible before under the earlier theory. And I've seen, we mentioned that Sabine Hassenfelder video, and there's other stuff out there, if you dig around, that kind of discounts this whole idea that they have negated the Big Bang Theory. They'll come up with something else. But as Sabina says in that video, you can write theories till the cow comes home. That doesn't mean it's real.
Yeah. I actually think that that we're a long way from fully understanding what recessional velocity is, the speed at which distant objects are moving faster and faster away from us. That leads to a quantity we call the redshift. I think we're still a ways away from really understanding that. I think that we're going to find that these distant galaxies that look like they've formed earlier than they should have are the result of a mistaken idea we have about the age of the universe and how we gauge it. And so we'll see. Let's see if I'm right.
And so much of cosmology, I poo-pooed dark energy and dark matter in the past.
Yeah, you
do. You have to keep in mind that they are just placeholders for trying to explain something that they don't understand.
Right.
That's right. That's right. And honestly, dark matter, on the other hand, I think dark matter is probably a real thing. There's really enough evidence to indicate there's something out there that's causing galaxies to spin almost like a rigid disk in ways that we don't expect. Okay.
Yeah. And some of that is older ideas like primordial black holes and stuff, I would have to think is at least a simpler explanation than some of the really exotic stuff they're trying to dream up. It's just there's gravitational effects that we don't know where they're coming from.
I agree with that, and that's one of that's now you know why I do astronomy. I absolutely love it, and for this very reason. There's nothing better than going into an astronomical mystery with an open mind and willing to just explore and enjoy everything that's to come. So I have to say, I need to thank all of you for coming tonight and spending time with Daryl and myself and Tara. It looks like the weather may support a stream right on the heels of this show. And Daryl, if you'll have us, Daryl, I think if you'll have me, Daryl, you might want to consider coming in at 11:15 or so. I see a cloud bank coming in, and I'm really hoping that that's just going to pass quickly. But we'll see. But right now, it's part of the plan, and it doesn't have rain in it, so that's a very good thing.
Okay. Yeah, if you do it, I'll be happy to tag along.
All right.
We're out of time.
I know we are.
We're out of space.
Right. It's about time. It's about space.
About space.
All right, guys. Thank you for coming, and we'll see you next week on Sky Tour Radio. And on behalf of Daryl and Tara, I want to thank you for being here, and you guys have a good night.
Good night.
Bye.